In this episode, we build directly on the idea that storage exposure usually comes from small choices that quietly become long-term reality, and we focus on the lever that controls most of those outcomes: permissions. Storage permissions are simply the rules that answer who can do what to which data, and in cloud environments, those rules can be surprisingly easy to make too broad without realizing it. The good news is that you do not need to be an expert to understand the core strategy, because the strategy is mostly about being specific and being consistent. Least privilege is the habit of granting only the minimum access needed to do the job, no more and no longer than necessary. And tight data boundaries are the habit of separating data so that a mistake in one area does not automatically spill into everything else. When you combine those habits, you get storage that is easier to reason about, easier to audit, and far less likely to become publicly exposed or widely shared by accident. Before we continue, a quick note. This audio course is a companion to our course companion books. The first book is about the exam and provides detailed information on how to pass it best. The second book is a Kindle-only ebook that contains 1,000 flashcards that can be used on your mobile device or Kindle. Check them both out at cyber.author.me in the Bare Metal Study Guide series. A useful place to start is to separate storage permissions into three simple dimensions: identity, action, and scope. Identity means the person or system that is trying to access the data. Action means what they are trying to do, like read, write, delete, or list. And scope means exactly which data objects or locations those actions apply to. Beginners often focus only on identity, like asking whether a user has access. But the real safety comes from narrowing action and scope as much as possible. For example, if a system only needs to read a set of images, giving it read access to a single folder is safer than giving it read access to the entire storage account. If a user needs to upload files, giving them write access without delete might be appropriate, while giving them full control might invite accidental damage. The simplest way to think about least privilege is that every extra permission is another way for a mistake to happen, another way for malware to spread, or another way for an attacker to turn stolen credentials into impact. Tight boundaries make those extra permissions harder to accidentally grant across unrelated data. Least privilege sounds obvious, but it fails in real life for predictable reasons, and understanding those reasons helps you design around them. One reason is convenience, where teams under time pressure grant broad access to make a problem go away, especially when they are unsure what the minimal permission set should be. Another reason is fear of breaking things, where people hesitate to remove permissions because they worry it will interrupt a workflow they do not fully understand. A third reason is shared environments, where many projects use the same storage and nobody wants to slow down progress with careful scoping. These pressures cause permission creep, where access gradually expands over time but rarely shrinks, even when the original need disappears. Least privilege is not a one-time achievement. It is a continuous correction against creep, and that is why boundaries matter so much. If the environment is designed with separate spaces for separate kinds of data, then granting access to one space does not accidentally grant access to everything. Tight data boundaries start with the idea that not all data should live under the same umbrella, even if it would be simpler from an operational point of view. Boundaries can be created by separating storage by application, by environment, by data sensitivity, by customer or tenant, or by business function, and the best choice depends on what kind of mistakes you want to prevent. If you mix test data and production data, a permission that seems harmless in a test context can leak real customer information in production. If you mix internal operational logs with public marketing assets, a permission set built for public distribution might expose internal detail. If you mix data from different customers, a bug or permission error could cause cross-customer access, which is a serious trust and compliance problem. Tight boundaries reduce the blast radius of a permission error, meaning the worst-case impact is limited to a smaller slice of data. For beginners, blast radius is a powerful mental model because it turns abstract permissions into concrete consequences. Once you have boundaries, you need consistent patterns for who gets access, and this is where roles and groups become essential as concepts, even without getting tool-specific. Managing permissions for each individual identity directly is hard to maintain and easy to misconfigure, especially as teams grow and projects change. Instead, Durable least privilege often uses role-like groupings, where a role represents a job function such as read-only viewer, data uploader, or backup operator. Identities are assigned to roles, and roles are granted permissions to specific scopes, which makes it easier to review access and easier to remove access when someone changes jobs. This approach also makes access changes more intentional, because adding a user to a role is a meaningful event you can track. It is also more consistent, because the same role can be applied across multiple boundaries without reinventing permission sets each time. The beginner takeaway is that least privilege is not just about reducing access. It is about making access understandable and repeatable. A common area of confusion is the difference between read access and list access, and it matters because listing can leak information even if the data itself cannot be read. List access might allow someone to see object names, folder structures, timestamps, or metadata that reveals sensitive details, like customer identifiers or internal project names. If an attacker gains a foothold, being able to list storage contents helps them target what to steal, what to delete, or what to corrupt. Even for legitimate users, list access can broaden what they discover, which might violate the principle of only knowing what you need to know. Least privilege means considering whether a user truly needs to browse everything, or whether the system can provide access to specific objects through a controlled path. Tight boundaries help here too, because even if list access is needed in one boundary, it does not automatically reveal the structure of all other boundaries. This is one of those small details that separates shallow security from thoughtful security, because it focuses on what information is exposed by permissions beyond the obvious download action. Another critical idea is to treat write and delete privileges as high risk, because they can turn access into destructive impact. Read exposure is about confidentiality, but write and delete touch integrity and availability, which means they can interrupt services, destroy evidence, or enable tampering. If a system has write access to a storage location that hosts important files, an attacker who compromises that system can alter those files, potentially feeding malicious data into other parts of the environment. If delete is widely granted, ransomware and sabotage become easier because attackers can erase backups or wipe critical assets. Least privilege often means separating roles so that the identity that reads data is not the same identity that can delete it, and the identity that writes new objects is not necessarily able to overwrite existing ones. Tight boundaries also support safer write patterns, because the place where new uploads land can be different from the place where validated content is stored. Even as a beginner, you can recognize that giving one identity full control is like giving someone the keys to every door plus permission to change the locks. Permissions also intersect with the idea of inheritance, and inheritance is a frequent source of accidental overreach. Inheritance means that a permission set applied at a higher level can flow down to child folders or objects, which is convenient but dangerous if you do not pay attention to where boundaries truly begin and end. A user might be granted access to a parent container for a narrow reason, and suddenly they can access everything under it, including data they were never meant to see. Or a public access setting might be enabled for a certain subset of objects, but because of the way inheritance is configured, it applies more broadly than expected. Least privilege encourages you to design the hierarchy so that inheritance works for you, not against you, meaning the safe default is inherited and exceptions are isolated. Tight data boundaries often mean creating separate top-level containers for different sensitivity categories so that inheritance cannot cross those lines. The beginner-friendly lesson is that structure and permissions are linked, and sloppy structure makes even good intentions risky. Least privilege also requires disciplined ownership, because if nobody owns a storage boundary, nobody feels responsible for reviewing and correcting access. Ownership does not have to mean one person doing everything, but it does mean someone is accountable for knowing what the storage is for, who should access it, and what should happen when the project changes. Without ownership, permissions tend to drift, and drift is where exposure happens, because old access remains long after the original team has moved on. Tight boundaries make ownership easier, because each boundary can have a clear purpose and a clear set of expected roles. Ownership also supports the idea of periodic access review, which is the habit of looking at who has permissions and confirming that each permission still makes sense. Reviews sound bureaucratic, but they are one of the only reliable ways to fight permission creep over time. In beginner terms, reviews are like cleaning out a closet so that old keys and old passes do not keep unlocking doors forever. Another major element is separating human access from system access, because they often have very different risk profiles and should not share the same permissions. Humans might need access for troubleshooting, investigation, or content review, and that access is usually occasional and interactive. Systems might need access continuously, such as reading configuration data, writing logs, or storing output artifacts. If you give humans the same broad permissions as systems, you increase the chance of accidental changes, and you make stolen human credentials more valuable. If you give systems the same broad permissions as humans, you increase the chance that a single compromised system becomes a master key. Least privilege means each system identity gets only what that system needs, scoped to the smallest boundary possible, and each human identity gets access that matches their job and can be removed when the need ends. Tight boundaries help ensure that a system for one application cannot automatically read or write storage for a different application. This separation is especially important in cloud environments because automation makes it easy for system identities to act at scale. As you think about tight boundaries, it is also worth understanding the difference between boundaries that protect against accidents and boundaries that protect against attacks, because you usually want both. Accident-focused boundaries limit the impact of a well-meaning mistake, like granting a permission too broadly or sharing a folder without realizing what is inside it. Attack-focused boundaries limit the impact of a malicious actor, like an attacker who stole credentials or malware that is trying to spread. In practice, the same boundary design supports both, because both accidents and attacks exploit overly broad access. If the environment is flat, a single error or compromise can reach everything. If the environment is segmented, a single error or compromise is contained. That containment is not just about confidentiality. It is also about protecting backups, logs, and critical operational data from being deleted or tampered with. Beginners sometimes think segmentation is only a network concept, but segmentation of data and permissions is just as important and often easier to implement consistently if you design for it early. One of the most practical ways to evaluate storage permission safety is to ask a small set of questions that force specificity, because vague access is almost always risky access. Who exactly needs this data, and can we name the identities or roles rather than using broad categories? What exactly do they need to do, and can we avoid granting write, delete, or full control if read is enough? Which exact dataset or boundary do they need? And can we avoid granting access to parent containers that include unrelated content? For how long do they need it? And is there a natural end date or review point? What happens if these credentials are stolen? And how much damage could be done within this boundary? These questions are not meant to slow teams down. They are meant to create a durable habit of narrowing access by default. Tight boundaries make the answers cleaner, because the scope question becomes easier when boundaries are aligned with purpose. When you put all of this together, controlling storage permissions becomes less about memorizing options and more about building a stable access posture that resists both drift and urgency. Least privilege is the discipline of shrinking permissions to the minimum, and tight data boundaries are the discipline of shrinking the scope of any permission to a well-defined slice of data. If you design boundaries that match sensitivity and purpose, you reduce the chance that a permission change accidentally exposes unrelated content. If you manage access through role-like groupings, you make permissions easier to review and easier to revoke. If you treat write and delete as high risk, you protect integrity and availability alongside confidentiality. If you account for inheritance, you prevent structure from quietly expanding access beyond what you intended. And if you build ownership and review habits, you prevent permission creep from turning yesterday's temporary access into tomorrow's incident. The big idea is that safe storage is not only about keeping outsiders out. It is about keeping access precise, explainable, and contained so that even when mistakes happen, they do not become disasters.
Thanks for listening. For more audio courses, daily newsletters, and more, please visit baremetalcyber.com.